comparing first ionization energy, and the first thing we're going to talk about is Downer group. Now, so now this is going to be. I mean, you have a lot of noise at your end. Can you mute the mic? I said so. The first ionization energy is Downer group. Now we're comparing ionization energies of different elements now. So down a group, what happens down a group? For example, I have group 1, lithium. Lithium has 3 protons in total. So it has a total of 3 protons and 3 electrons.
Yeah.
So here is lithium. And we're talking about the first ionization energy, which means we are trying to remove this electron, like the outermost electron. That's it. Below lithium is sodium. Sodium has 11 protons and 11 electrons. So it's 2, 8, and 1. And as you go further below in group 1, you'll meet potassium. Potassium has a total of 19 electrons. So there are 19 protons. Okay, and its electronic configuration is 2, 8, 8, 1. And 1. So we're moving down a group. What do you think is going to happen to the ionization energies as you move down the group? The first ionization energy, we're trying to remove just.
Does it decrease?
Okay, so it's going to decrease. First ionization energy decreases down the group, and what's the reason?
Because when you go down, there's more electrons, so there's more shells. So the electrons get farther away from the nucleus.
Okay, so one factor is there's more shielding.
Yeah.
Okay, so the nucleus is surrounded by electrons, so it's not going to attract the electron really far out. More shielding, and the second factor is obviously more distance as well. The electron is further away. Any other factor that's playing a role?
Is it because the atom is neutral, so it's like easier to remove it?
Yeah, but that's not going to be a factor because all atoms are neutral. So when you're comparing things, that's not going to be a factor, right?
Yeah.
I said, so one thing is going against it, and that is that as you move down the group, the number of protons are increasing.
Yeah.
So what you actually write is, I mean, there are two factors that are suggesting that it would be easier to remove electrons, right?
Yeah.
So ionization energy decreases. Why? Because as electron is further from the nucleus, And the other thing is that it's further from the nucleus and more shielded. Despite the fact that protons are increasing.
Yeah.
So, despite the fact that uh, protons or nuclear charge increases down the group. So, this last factor goes against it. The two factors that favor the decrease in ionization energies uh, further from the nucleus and more shielded, despite the fact that protons increase. Right? So, is this clear?
Yeah.
So this is pretty much it. Whenever you're being asked about ionization energies across, sorry, down a group, they always decrease.
Okay.
I said then there's another thing that you have to study about ionization energies, and that's across the period. What happens if two ionization energies as you move across a period? So first ionization energy across so comparing this across a period. Uh, and let's talk about period two first. There is lithium, then there is beryllium, then there is boron, and then you have carbon and nitrogen and oxygen
Yeah.
and fluorine and neon. So these are all the elements. In the second period, this is the second period. So this one, the first one has three protons and three electrons. So let me draw a few of them. So three protons and you have three electrons. We can draw carbon as well, which is six protons,
Mhm.
and it has a total of six electrons. And similarly, we can draw fluorine over here, which has nine protons and a total of nine electrons. So, and let me adjust. So this is the trend. As you're moving across the period, you'll notice that. Okay, so I've drawn just a random bunch of atoms in the period, not all of them. One thing that you would notice is as you move across the period,
Yeah.
number of protons keep on increasing, and so as you move to the right, I can write the number of protons. Lithium has three protons, then beryllium has four, boron has five, carbon has six, and so on.
Yeah.
So the number of protons they keep increasing. So that would make it difficult to remove electrons because the electrons are going to be more strongly attracted, which is why elements on the right side they usually gain electrons. Why do they gain electrons? Because they always have more protons, right?
Yeah.
Which is why they're non-metals. Non-metals they like to gain electrons because they have a lot of protons. Fluorine has nine protons. Lithium, on the other hand, just has three protons. So lithium would not be attracting its electrons very strongly, but fluorine, on the other hand, would be attracting its electrons very, very strongly. So number of
Yeah.
protons increase. So ionization energy should increase, is higher. And similarly, what happens to shielding? Shielding remains constant. Like the outer electron in each case, there's exactly just one shell. I mean, if you're trying to remove one electron from each of the atom, there's exactly just one shell coming in the way between the nucleus and the outer electron. So the
Yeah.
shielding is constant. Shielding remains constant, so that's not really a factor. Same number of shells. What do you think about distance? What happens to distance of the electron from the nucleus?
Um, it stays about the same, doesn't it? Because they're all in the same period, so it has the same number of cells.
Exactly, they have the same number of shells, and I mean, the electron is in the same shell, so there shouldn't be any effect on distance, but distance slightly decreases. Why? Because 9 protons are going to attract the electrons more strongly, right? So the electrons would be closer to the nucleus.
Yeah.
I mean, 6 protons would not be attracting its electrons that strongly. 3 protons would not really be attracting its electron very strongly, so it would be further away. So
Yeah.
because as you move to the right, you have more positive charge in the nucleus, more protons. So the electrons are kind of tightly held together. So the size of the atom gradually shrinks.
Okay.
So distance slightly decrease. I mean, you have more protons, so there's going to be more attraction for outer electrons.
Yeah.
And if the distance slightly decrease, there's going to be higher ionization energy. Like it's going to be closer to the nucleus, so more difficult to remove electrons. So basically, all factors are suggesting that ionization energy increases across the period.
Yeah.
Is this clear, Aman?
Yeah.
So all factors are suggesting that ionization energies are going to be higher if you move to the right. So let's sketch these ionization energies. So we have lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So on the horizontal axis, we have these elements, and the ionization energy increases across the period. But what happens is lithium has the lowest, then there's beryllium, then at boron there's a slight dip, then you have carbon and nitrogen, and after nitrogen at oxygen there's a slight dip, and then you have fluorine and neon. So
Um,
it's something like this. It is. I mean, the general trend is that it's increasing.
okay.
So the general trend is that it is increasing, except that there are dips at group 3 and group 6. So dip in first ionization energy at group 3 and group 6. So is this, I mean, the general trend, is that clear?
Yeah.
I said now you have to explain. So this is across the period, right? As you move across the period, number of protons keep on
Yeah.
increasing, and the shielding remains constant, and the distance slightly decreases as you move across the period. So the general trend is that the graph is going to go up. And but what happens after? Oh, why? But the first thing is, why are there dips at group 3 and group 6? We need to explain that. So so explanation for the dip in ionization energies at group 3. Now, the explanation for that is that if you look at group 1, let's start with lithium. You do know how to write electronic configurations, right?
Yeah.
So, lithium has 1s2 and 2s1, right?
Yeah.
Beryllium, 4 electrons is 1s2
Two S two.
and 2s2. Is this clear?
Yeah.
Actually, now in both cases, lithium and beryllium, the orbital doesn't really matter because you're removing electron from the same orbital, same subshell. Like it's a 2s subshell, 2s subshell, so that doesn't matter. Now, when you reach boron, the one at group 3, it has 5 electrons. Its electronic configuration is 1s2, 2s2, and then 2p1. So when you're removing electron from boron, you're removing an electron which is further away from the nucleus, right? Is this clear?
Yeah.
So you're removing electron from a 2p subshell, which is a higher energy subshell, which is further away from the nucleus. So it kind of becomes easier to actually remove electrons from boron. So there's a dip. It becomes easier. Why? Because you're removing an electron which is slightly further. Now between these two, this wasn't a factor because you were removing electrons from the same subshell. But now you're removing an electron which is slightly further away. So it kind of becomes easier to remove electrons. So the
Yeah.
explanation is that in boron, electron is removed from a higher energy from a higher energy 2p subshell, which is further away and more shielded. And more shielded. So it's kind of easier to remove electrons compared to the 2s subshell.
Yeah.
So compared to the 2s subshell in beryllium, hence ionization energy decreases. Hence boron has lower first ionization energy compared to. So is this clear, Amal?
Yeah.
So then you have the other dip, which is at group 6. I mean, when you reach oxygen, there's another, instead of following the trend, there's a decrease again at oxygen. So now the next part is we need to understand explanation for the dip in at group 6. Now what happens at group 6? Like let's pick carbon. Now carbon has a total of 6 electrons, so it's it's 1s2, 2s2, and 2p4. Not carbon. Just wait 1 second. Carbon has a total of 6 electrons, right? So that's two left.
Yeah.
So that's 2p2, which means that 2px, 2py, and 2pz orbitals. That's 1, 1, and 0. Then the next one from carbon is nitrogen. Nitrogen has a total of 7 electrons. So it's again 1s2, 2s2, but now it's 2p8, 2p3. So 2py and 2pz. So that's 1, 1, 1 each. Then there's a dip at oxygen, 8 electrons. So 8 electrons would be 2p4, so it's going to be 2px, 2, 2py, 1, and 2pz, 1. Now, the issue with carbon is that when you're trying to remove electrons, you're removing electron from a single 2py. I mean, you have a 2p orbital which only has one electron. If you're trying to remove electron from nitrogen, you're removing electron from a 2p orbital which only has one electron. But when you're trying to remove electrons from oxygen, the electron is being removed from a 2p orbital which is completely full. So why does it become easy? Because if like there's this nucleus and there's a 2p orbital and that 2p orbital has two electrons in it. So what would the electrons do? They're going to repel each other. So if there's a 2p orbital with two electrons in it, both electrons are going to repel each other and they're going to kick each other out of the orbital. So it would be much easier to remove electrons from a full 2p orbital, right? Because of the mutual repulsion between them. Amal, is this point clear?
Yeah.
Okay. In the previous case, the 2p orbitals were not full. They were all half filled. They just had one electron each. So there was no repulsion. There was no mutual repulsion. Like you had 2px, it just had one electron in it. You had 2px, 2py, or 2pz, each one had just one electron in it. But when you reached oxygen, the 2p orbitals, they started having two electrons, and the two electrons would repel each other, and so it would become easy to remove electrons. So what you're going to write is that in oxygen, electron is removed. So in oxygen, electron is being removed from a paired 2p orbital. So due to spin pair repulsion, the electron-electron repulsion is called spin pair repulsion due to spin. So due to
Yeah.
spin pair repulsion, it becomes kind of easy to remove electrons. And we can also write while in nitrogen,
Mm.
electron was removed or was being removed from a half-filled p orbital. So no spin for repulsion there.
Mm,
Is this clear?
yeah.
So I'm going to sum up what we just did. What we did was that we studied the trend across a period, like what happens to ionization energies across a period. You had more protons moving to the right, and the shielding was constant, and the distance was slightly decreasing. So the general trend was that ionization energies would kind of increase across the period. Uh, but then there were dips at group 3 and group 6, and these
Yeah.
dips would be there in every period, not just the second period, every period. And the reason for those dips was at group 3 was that all of a sudden you're trying to remove electron from an orbital which is slightly further away, from a 2p orbital. It would become easier to remove electrons. And the dip at group 6 was that before group 6, you're removing electrons from 2p orbitals which are singly filled. But then when you reach oxygen, you're removing electron from a 2p which is paired.
Yeah.
So because of the pairing, because of the repulsion, there are two electrons in the same orbital, they're repelling each other, so it kind of becomes easier to remove electrons. I said
Okay.
then we're gonna do one more thing, which is like after neon. What happens after neon? Like if we continue sketching this graph, let me. I said so. What's going to happen after neon? After neon, I'm going to move to the next period, which is going to be sodium.
Yeah.
So this is neon, then I have sodium. So the same trend would start repeating again. Sodium, then magnesium. Then after magnesium, there's 13 would be aluminium. Then 14 would be silicon. 15 would be phosphorus. 16 is going to be sulfur, chlorine. And you have argon. Now, this was period number 2 up till this point.
Yeah.
So this was period number 2. Then period number 3 starts. Now the trend is going to be exactly the same, except that it's going to be lower. At aluminium, there's going to be a dip. Then there's going to be silicon and phosphorus. Then at sulfur, group 6, it's going to be a dip. So it's going to be the same trend,
Yeah.
except it's going to be lower. Why do you think in period number 3 the trend is the same, but why is it lower? Why do you think it's lower?
Um, because I think when you start period 3, there's another shell, like
Exactly.
this, so it's easier to remove it.
Okay, so because you're actually when you're moving to period 3, you're actually moving down the group or
Yeah.
downwards. So there's an extra shell, and the electrons, all the electrons are like further away from the nucleus, like compared to sodium. Uh, so basically, you can compare that every atom is one. I mean, you're moving down the group. So,
Okay.
so which is why. So same trend, but lower
Mm,
due to an Terrestrial. So now we are done with ionization energies. What we're going to do now is we're going to try and do some questions related to this. I'm going to send you the worksheet as well. Just one second. Let me. Just one second. I just so ionization energies.
Yeah.
Now, a lot of these questions, I mean, the topic is not that difficult, but the questions are going to be tricky. Uh, so the question is, which element has the second smallest atomic radius and the third lowest first ionization energy in its period? So, so first thing, third lowest first ionization energy in its period across the period. He's talking about across the period. So I'm going to bring this up again. Which group do you think the element is in? I mean, across the period, it has the third lowest ionization energy. Like
Um,
you have the whole thing in front of you. So which element, which out of these, which element has the third lowest?
is it
I mean, let's think that it's in period two. So in period
yeah,
two,
okay.
which one has which element out of all these has the third lowest ionization energy?
Oxygen?
Third lowest. I mean, third lowest. What does that mean? Like
Um,
third lowest means from the bottom. The third from the bottom. Oxygen is how is oxygen the third lowest? Actually, which one is the lowest? Tell me which one is the lowest. It's lithium.
lithium?
Lithium. So that's the lowest, right? Which one is the second lowest?
Um, beryllium?
Not beryllium. I think it's boron.
Yeah,
Okay. And what about the third lowest? I mean, remove lithium and boron now. Which one is the third lowest? It's going to be beryllium, right?
yeah.
So basically, it's the element in group two. That's the third
Oh,
lowest.
okay.
Even if you had chosen this period, it would be the same. The third lowest would have been magnesium, group two, right?
Yeah,
Because the lowest would have been sodium. The second lowest would have been aluminium. Third lowest would have been magnesium. So
yeah,
basically, when he's talking when he's talking about the third lowest first ionization energy in its period, he's talking about group two, right?
yeah.
So so he's talking about an element from group two. And the first one, second smallest atomic radius in its group. What does that mean? Like in its group, the group is the vertical arrangement. So second
Yeah.
smallest atomic radius, which element would it be? And we know it's group two.
Um, the
Like
sodium. What
the
would it
second
be? Magnesium, magnesium.
exactly, it's going to be magnesium. I mean, let me here's this pure table. So is this clear that it's going to be a group two element, right?
Yeah,
And the second smallest atomic radius would be magnesium, right? Because the smallest would be the
yeah.
first. Okay, so it's going to be magnesium. This is magnesium. I'm going to let's skip this one for a second. I mean, we're going to come back to this later on. So, definition, which terms can be illustrated by an equation that includes the formation of a positive ion? Uh, the first ionization energy is results in the formation of a positive ion, right? Is that clear?
Yeah.
Let's skip the other two. So over here. Now look over here. They're asking what could be element X. They're saying that one of the element, there are four elements. He's given you the first ionization energies, and it's according to the atomic number. So you're basically moving across the period. Like,
Yeah.
as I say, you're basically moving across the period because atomic numbers. I mean, this side is they're arranged according to their atomic numbers. Now, if I which portion of this, I mean, you're moving according to the atomic number, right? Lithium is 3, then 4, 5, 6, 7, and so on. So which portion of the graph do you think this uh, question belongs to? Like, here's this. I mean, they've given you a portion of the ionization energy graph.
Yeah.
So in the one that I've sketched, which section is this?
I think it's from like chlorine to magnesium, the middle bit.
Okay, this part, right?
Yeah.
I mean, so because it's showing a depth, right?
Yeah.
I mean, there's rise and then there's this giant drop. So that happens when
Yeah.
the period changes, when a new period shows up. So this must be group one. This one
Yeah.
must be group two. This would be the noble gas, group eight. This must be group seven,
Yeah.
right? So this section over here. I mean, this one, then there's this giant dip, and then these two. So, so the question is, one of the element reacts with hydrogen to form a covalent compound. So it's forming a covalent compound of the formula HX. So which elements out of A, B, C, and D do you think is this compound?
Um.
It's forming a covalent compound. So can it be group one or group two?
No.
Because they are metals, right?
Yeah.
They don't form covalent compounds.
Yeah.
So what are you left with? You're left with a noble gas. Would it form a compound?
No.
Okay, so the only option that you're left with is A, and
Yeah.
that's probably chlorine or someone from group 7.
Yeah.
And HX would probably be HCl or something, HF or HI, etc. Is this clear?
Yeah.
So then you have he's saying question number 33 that its outer electron is in the fourth principal quantum shell. So which period does the element belong to?
Um.
I mean,
Period four.
it's in the fourth shell, right? So it's in period number 4. This is period number 4,
Yeah.
like from potassium to krypton over here.
Yeah.
So this is period number 4. The other thing where's the question? The other thing is, the other thing is saying is that it has a higher first ionization energy than calcium. So compared to calcium. So let's open the periodic table again. Calcium is over here. So do you think potassium is going to have a higher ionization energy than calcium or not?
No.
So group one, I mean, what's the trend? The trend is usually uh, the first one has the lowest, then there's a rise, then there's a slight dip, and then it continuously increases, right?
Yeah.
So if you look at the question again, uh, these three elements, First thing is you need to have a periodic table with you. It's bromine. Bromine, is it in bromine is here, right?
Yeah.
I can see bromine in period 4. Krypton is also there. So these two are going to have much higher ionization energies compared to calcium, right? Because calcium
Yeah.
is in group 2. What was the other element? There was xenon.
Yeah. So
So xenon cannot be the right answer because if you move down the group, then all of a sudden ionization energies they decrease.
so both of them are the right answer, bromine and krypton.
Uh, yes, bromine and krypton. I mean, in these questions, you have one and two both can be
Okay.
correct. I mean, the multiple options can be correct, except xenon can't be correct. Why? Because you move it's down the group,
Yeah.
so the ionization energy is going to be lower.
Okay.
So now this is again a graph of across the period. Like this is across the period, then there's a dip, then across the period dip. So this is a graph of elements, consecutive elements. The first ionization energy is plotted across the period. Now, which statements are correct? P and X are in the same period of the periodic table. P and X. Here's P
No.
and here's X. What's
Mm,
the answer?
no.
Okay, obviously not because this is one period and this is another period.
Yeah.
The general increase from Q to X is due to increasing atomic radius. Q to X. I mean, why do ionization energies generally increase across the period?
Because of the there's more protons
Okay, because they're more.
and
Ex- that's the number one factor, right?
yeah.
And this statement is incorrect anyways because the atomic radius actually decreases across the period.
Yeah.
Okay, this is what we discussed that across the period the number of protons are increasing, the shielding remains constant, the distance actually slightly decreases across the period.
Yeah.
The small decrease from R to S is due to the decreased shielding. So why was there a dip at group 2?
Um because that was the first electron in the new subshell, so it was easier to remove.
Okay, because it was uh, let's see. Why? Because it was further away and
Yeah.
more shielded as well,
Yeah.
right? I mean, there were more shells coming in more subshells coming in the middle, so it
Yeah.
was kind of further away, more shielded. So the question states that there is decreased shielding. Uh, there was in fact increased shielding, not decreased.
Yes.
Okay, there was actually more shielding. I said a small decrease from U to V is due to repulsion between paired electrons. Like, why was there a dip at group 6?
Yeah. That one's right. The last one.
Okay, that was because of, so the last one is correct because that's what we discussed that when you move to group 6, all of a sudden your p orbitals are full. And the
Yeah.
electrons, there are too many electrons in the same orbital and they repel each other and there's repulsion. So, Amal, is this clear?
Yeah.
Okay, so I'm going to send you this worksheet
Okay.
and I'll send it on the same WhatsApp number. I think it's your father's WhatsApp number, TK.
Yeah. It's my dad's.
Okay, I'll send a worksheet on that, and I'll ask you to do. I'll specifically ask you to do a few questions, TK.
Okay. That's fine.
Chalo, TK. Okay, then take care, Amal.
Okay, thank you.
Allah Hafiz.
Thank you.